So let's begin this time with a question. What if I have a proton? And I ask you, is that a fundamental particle? So can I split this particle any further? Well, in fact, it seems we can. A proton, a neutron, and many other particles, they constitute of quarks. And that's what we're going to discuss about today. So all particles which are made of quarks are called hadrons. And there are two types of hadrons. The ones which contain two quarks and the ones which contain three quarks. There's no other possibility. You cannot find quarks just alone in the universe. They will always be in pairs or trios. When they are in pairs, we call them mesons. And when they are in trios, we call them baryons. Those are probably some new names, but there are some particles that you already know which would fit in those categories. So, for example, both the proton and the neutron, they are baryons. They consist of three quarks each. And just to let you know, proton is composed of up, and down quark. And we'll discuss that in more detail. And the neutron is given by up, down, down. So those would be the quarks which are inside of this proton, which make this proton. So the proton is in fact the combination of those quarks. We call it proton. We could just say up, down, those quarks together. It's the same thing. Now, mesons, we've seen some particles in the previous class. Pions are an example of mesons. So pions, up and anti-down. So this is the anti-quark to down. You've got quark up, there's anti-up. You've got quark down, there's anti-down. There's also other types of quarks. For example, kaons, they will not only contain the up quark, but they will contain something called a strange quark, which was found in 1947, was discovered in 1947. And well, there's a special reason for this name, but it's just because it did not match the expectations of the scientists, so they called strange. And nowadays we do have conservation rules for those, so it's an useful flavor of quark. So if I built a table here with all quarks, I could just have up, down, charm, strange, top, and bottom. So up and down, they are quite old. They are from the beginning of last century. Now, strange, as I told you, was discovered in 1947. The top quark was in 1995, and the bottom one 1977. So, for example, the top one is quite recent if you think about human history. Now, those flavors of quarks, they don't mean actually anything special. What do I mean by that? Well, even though we call them flavors or colors or those names, they have no physical significance. So they have no physical meaning besides making it possible for us to distinguish between them. So it's not that up is an arrow pointing upwards or anything like that. It's just a name that we have given. So we're able to describe them and differentiate between the down quark or the charm quark or top or any other one. So it's important to notice that each quark will have a different charge, a different mass, and a different spin. So let's take, for example, the up and the down quark. So if we were to write down the charges, the mass and the spin for both of those, the up quark has a charge of plus 2/3, and yeah, it's plus 2/3 the charge of a proton. Now the down quark, however, owes a charge of negative 1/3. The mass of the up quark is 5 mega electron volts per speed of light squared, whereas the down quark is 8 mega electron volts per c squared. The spin of the up quark is plus 1/2, and the spin of the down quark is minus 1/2. So let's take as an example our proton. So let's assume that this is our guy. Protons, they are composed of 2 up quarks and 1 down quark. So up, and down. So to check the properties of the proton itself, we will have to add the properties of the quarks that consisted. So the charge of 1 up quark is plus 2/3. So each of those ups, they will add 2/3 to the charge. However, there's 1 down quark, and the charge of a down quark is negative 1/3. So negative 1/3. The result here will be plus 1. So the charge of a proton is plus 1. That's what we expect. So we can see that we can combine, and we'll see that we can combine quarks in several different ways as long as the charge is an integer number. So as long as it's 1, negative 1, or 0. So yeah, that's the proton. What about the spin of the proton? We could also do that. So the spin, we just work it out the same way. So plus 1/2 2 times, because you've got 2 of them, and negative 1/2 just once. So that's plus 1/2, and that's the spin of a proton. So if I asked you the properties of a neutron now, even though if you did not know that a neutron is, well, neutral charge, right? Or you might not know the spin of the neutron, I don't know. So the neutron is composed of 1 up quark and 2 down quarks. So the up quark has a charge of plus 2/3 and the down quark negative 1/3. So we can easily visualize that the charge will cancel out. This is the up quark, this is 1 down quark, this is the other down quark. So 2/3 minus 1/3 minus 1/3 is 0. What about the spin? Well, up quarks, they have a spin of plus 1/2, and down quarks, they have a spin of negative 1/2. So the spin here will be 1/2 minus 1/2 minus 1/2, which is negative 1/2. So we can see that those properties, they're different, even though there are the same quarks involved. So by combining different quarks, we may obtain the particles that we have discussed so far. You can also check here that the down quark is more massive than the up quark. So since our neutron here uses 2 down quarks and our proton only has 1 of them, we would expect our neutron to be more massive, slightly more massive, right? And that actually matches with the properties that you can find in your physics data booklet. So really quickly, let me talk to you about the lambda particle, and also how did we came up to find the strange quark. So the lambda particle was measured to have 10 to the negative 10 seconds of life in a cloud chamber that looked a bit similar to this one. All right, there's no point here in delving too much into this, because the point here is the time, the measurements that they detected, that they measured for the life of this particle was this, 10 to the power negative 10. However, the prediction, the theoretical prediction, was for it to be 10 to the power of negative 23. So this was a very strange difference. And as funny as it sounds, that's exactly what resulted in our idea of the strange quark. So this strange quark, this property, was dubbed strangeness, and basically led to the assumption that there is another quark which makes the life of this particle longer. It should only last about this in theory, but in practice we have found this much. And by comparing with other particles later on, we found that, yeah, the strange particle is going to do that. And any particle that contains this quark, we might notice something like that. So just for some dates, the Lambda particle was discovered in 1947, and there's also some other less discussed particles like the psi, or simply psi, right? Which is a baryon. And again, baryons, they've got 3 quarks, just like protons, neutrons. And we also have an omega. So this is the omega baryon, also 1964. And that's also a baryon. In this case, this baryon is strange. And that's fun. So, summarizing everything that we have discussed so far and putting a few things that we're still about to talk and discuss, you can see here this table, and you should identify most of those things. So here in the upper left, we've got quarks, and we've got all definitions here: mass, all information, mass, charge, and spin. So if I want to analyze, let's say, the up quark, spin is half, charge is 2/3, and well, there you go. Now you can also compare with other ones, like, oh, this is minus 1/3, right? That's the charge. The charge of a tau particle, tau lepton, is -1. A mu1 has a spin of a half. So you don't have to memorize those values. Alright, probably up and down, you will remember those things, but you're not really expected to memorize any of that. What you should understand is that this table is actually folded, let's say, because for every quark that I have here and for every lepton that I have here, I will have an anti-quark and I have an anti-electron. We usually denote anti-particles just by putting a bar on top. So for example, this would be an anti-down quark. And since we have the properties of the down quark here, we don't have to put it in another slot. There are some tables that give you some more information, but you don't have to, because the anti-down quark will basically be a down quark with everything flipped. So the charge will be opposite and the spin will be opposite. So, as I've mentioned before, quarks can never be found alone in the universe. They are always bound with other quarks, either in pairs or trios. In pairs, again, we call them mesons, and in trios we call them baryons. So why is that, and what would happen if we tried to split 2 of those quarks? So what actually happens is that you create another pair, 2 other pairs. So let's say that you've got here 2 quarks, it doesn't matter which ones, but you're trying to pull them apart. So you're exerting some force, you're putting some work here, you're putting energy to split them apart. And theoretically, well, according to everything that we've studied so far, before we dealt with quarks, we could split particles if we gave them enough energy. But what happens here is, as they get further and further apart, you will in fact create another pair here. So let's say that, for example, this is a down and I don't know, let me look for some specific and realistic example. So let's say that this is a positive pion. Okay, it's just a pion. So pion consists of an up quark and a down quark, an anti-down quark. So when we try to split those two together, what we'll eventually do here is create another pair of quarks in between. So at the end, we will again have pairs of them, right? And then you'll have here an up quark with something else and an anti-down quark with something else. And most importantly, those two, they will be some particle and anti-particle pair because they've been created right out of the blue. So to create that with energy, you need to create a pair of particle and anti-particle. So when you try to get quarks, when you try to confine a quark, you cannot. You basically create another pair of quarks. And that's called quark confinement. So this means that differently from neutrons, protons, electrons, everything that we have been discussing so far, we cannot get quarks alone. We cannot separate them completely and have one quark just sitting there still. Now, so far we have discussed about a lot of things. We have discussed about the history of those particles, how did we get to know those particles, and now we should try and understand, okay, we have applied before some conservation rules when we were trying to predict things which would happen. And now we can still use some conservation rules, however we'll have some quite different conservation rules, and I'm going to show you those now. So, differently from when we were dealing with larger things, here we will have three conservation laws. One of them is conservation of charge. The other one is conservation of baryon number. And the third one is the conservation of lepton numbers. There's also the conservation of strangeness, but that's a bit different. Now, conservation of charge, that's fairly simple. We are all okay with the concepts of charges. We have seen some quarks which have a charge of plus 2/3, some with negative 1/3. So if, for example, if we have this combination here, plus 2/3, negative 1/3, negative 1/3, our charge would be 0. So if before one reaction our charge is 0, then after that reaction it will still have to be 0. It cannot change. So if you had no charge before, let's say a neutron, and then it decays through beta decay, it will then produce a positive charge, which is a proton, and a negative charge, which is an electron. If you sum those charges, it's still 0. Even though there's an anti-neutrino somewhere, it doesn't matter because there's no charge associated with it. Now, baryon numbers, basically every baryon will have a baryon number of +1. So if you have, let's say, one baryon before some process, you will need to have the same baryon number after. So in the same example that I gave you before, if you have some neutron just decaying through beta decay into a positron and an electron, then your baryon number in the beginning is 1 because it's a neutron. Since a neutron is a baryon, it will have a baryon number of 1 plus 1. After the decay has happened, we still have a proton, and protons, they are also baryons, so they will also have a baryon number of +1. Now, lepton number is really similar to baryon number, but it's the property of leptons. So electrons, for example, they do have leptons. Any particle that, leptons, right, they will have lepton number of +1. And antiparticles, any antiparticle, they will have -1 here, both for baryons, for lepton number as well. So in the same case, and let me just write it here. So you've got a neutron undergoing beta decay, becoming a proton plus an electron plus a antineutrino. Now, the lepton number before, since it's just a neutron, is 0. So the lepton number after will still have to be 0. And after the reaction, we do have an electron, which is a lepton. So the lepton number is +1. However, we also have an antineutrino. The antineutrino has a lepton number of -1 because it's an antiparticle. So when we add +1 minus 1, our lepton number at the end will also be 0. The only thing which is slightly odd about the conservation laws is the strange particle. So the strange quark is something completely different from the other ones, because if you do have a strange quark, then your strangeness is -1 for each strange quark that you have. And yeah, that's just the opposite, right? So strangeness is negative if you have them and 0 if you don't have them. And if it was obviously an anti-strange quark, then it would be +1 instead of -1. And this should also be conserved. In this case, a neutron, it has no strange quarks. Remember, neutron, let me write this in a different color. So the neutron is one of the baryons that we have studied, right? So neutron is basically up, down, down. And after decay, it becomes a proton, which is up, up, down. And we also have, obviously, the electron and the antineutrino. Now, up, down, down, there's no strange quark. So strangeness is 0 before, and strangeness has to be 0 after. So here, strangeness will be 0 before and after. So those are the conservation laws that you will have to check when you're working with decays or equations in such context. So conservation of charge, conservation of baryon number, conservation of lepton number, and conservation of strangeness. Now, for the end of this lesson, I would like to propose you some thinking process here, and it might be looked as a question, might be seen as a question, but it's not actually a question, it's just for you to think about it. So, what if a proton collides with a negative pion? And I'm going to tell you that negative pion is anti-up and down. So a proton has 3 quarks and a pion has 2 quarks. Now, show me that the collision products they can be a neutron and an uncharged pion. It's not hard to do, and you will basically have to work with your conservation laws and apply each one of them to verify. Now, there will be no strange quark here, so you might not need to worry about strangeness, but all the other conservation laws should be observed. So that's it for today. Next lesson, we'll be dealing with fundamental forces, exchange particles, Feynman diagrams, and the Higgs boson. And that should be it for this chapter, hopefully. All right, have a great day, everyone, and see you next time.